10 from the local guy and 10 from the chain willy-nilly whenever we want to. Let's instead do what they do in example 10.2. And just one little nuance difference, we're going to pick a time. And at this time of day, whether it's noon and rush hour or whether it's 3 in the morning, we're going to order one pizza from the local and one from the chain at the same time. And we're going to time them then. Now we've done a better experiment, right? We've controlled for that variability. We've controlled for the time of day or the rush hour. So it's just a tiny nuance. And it's the same data, except now I ordered it, assuming that, yeah, this one was the same time. That's how they did the book. And now we can go through and use this paired thing because they're not independent, right? This group and this group depend on each other because they were at the same time. We compare them, we can look at their difference. And if we ask the same question, is there a difference in the means? Go through that analysis, boom, 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 oh, yeah, there is a difference. And so the paired test is a better test, right? Why? Because you included a tiny bit more knowledge, right? We controlled for that variation. And if you look at the data, you can even see what happened. You can see that, well, look, if you go over here, here they were both fast, and here they were both slow. So when you pull all this together, you flush that, you kind of, you smear that out. Yeah, you average these two, and you didn't see the difference. But if you're taking a difference, well, they were both slow, but look, they still both have this same difference. They were both fast, but the difference, oh yeah, still around 3. So it was a more powerful test. So you can see how, and that's not that big a change. So you can start seeing how understanding of how you're going to do your statistics can help you do a better test. And in this case, completely change your decision. You did find the local one was faster and better because you didn't confuse the data by mixing the time of day in there. So the moral of the story is if you're going to do some statistical tests and you're going to analyze it by a certain way, think ahead of time what implications there are in how you do your test. Because I would submit to you that this isn't that hard to change. Yeah, the other way was a little easier. I ordered one pizza, I ate it. The next day I ordered another one, I ate it. So here I'm having to order 2 pizzas. And yeah, I'm having to order one from Domino's and one from the local guy. And I might have wanted both from the local guy or something. There's a little bit of changes, but in terms of trying to reach an understanding, no, that's not that much. Or wouldn't you have hated to have actually done the test this way, but not paired them together and just thrown them all in an Excel spreadsheet and not really kept up with which one was where, and you wasted that piece of information? Because it did add to your knowledge. So think about it ahead of time. Think about what you're going to do and construct your test appropriately. In fact, I would try to come up with my analysis before I do my test so that I don't make a mistake like that. So that was sort of, we were hanging out over here in the T world, right? Separate T, pooled T, paired T. Why? Because we're over here in the numerical world, right? And those are always the T tests unless we randomly happen to luckily know the population standard deviation. Now let's go on the other side of the world to the categorical, because why? Well, sometimes things are yes, no, good, bad, and ugly questions, and so let's do them. Remember, they always represent them pies because these are proportions. The proportion being the percent of the population that had the attribute you wanted, the percent that had high quality, the percent that voted for something. Anything like that. And so remember our assumptions, these are the same ones we had before. Instead of 30 tests, the number of things that have the characteristic need to be bigger than 5, and the number of things that do not have the characteristic need to be bigger than 5. Remember I made the comment, one of the 2 of these will cream the other, unless it's 50-50. And most of your things are, so if it's 95 or 5, one of them is going to be far exceeding the other will not. And it has to be the case for both populations, right? These kind of assumptions aren't startling, I think. I got to get enough samples from both populations on both sides of the fence. And so, hey, we're going to ask ourselves, You know, let's compare the difference in the proportions between the first sample and the second sample. And yeah, let's see. So let's see the null hypothesis. It's going to be that they're equal. We can pool the two samples. The pooled estimate for the overall proportion is this. Yeah, we're taking the, normally we would have had that as one proportion, that is the other one, and we're putting the two together. Yeah, X1 of the number of items of interest in samples 1 and 2, total number of samples. Okay, and here's our statistic. Remember, proportion 1, proportion 2, we're assuming these two are equal, that's a 0. Here's your standard error, the equivalent of your standard deviation for the population. And then it's calculating what each of these little guys are. Those are the individual proportions. So this is kind of the slide that where I could stop and answer that question I asked you the other day. Remember I said, you notice we never have a t-test for the proportion, right? The proportion is always the z-test. But over here in the numerical world, you know, we had z-tests sometimes and we had t-tests. Well, why we don't have another branch over here going down the t's and stuff like that? Well, remember, when we did the numerical stuff in chapter 8 or 7, it was 8, yeah, it was 8. The t-test arose or came up when we did not know the standard deviation of our population. The one case when we knew the standard deviation of the population because of the past, remember that's the case that's not very likely, but they said if you make it from the past, you were able to use the z-test. But any other time, you had to use the t-test because it had a broader spread. Remember, it spreads out, gives you a little more uncertainty. It's to reflect the fact that you don't know the standard deviation of the population. You get a little bit more uncertainty. Well, look, if we know, if we've made a sample measurement, there isn't any degree of freedom, if you will, in the variance here, right? The variance is calculated from the proportion. I mean, remember back in chapter, I think it was chapter 7, the variance or the standard deviation for the population proportion is what, pi times 1 minus pi over n. So once I think that was the equation, I wrote it down. Yeah, equation 7.7. So once you know the proportion, you also know the standard deviation. So that's why these categorical ones don't need that extra degree of freedom. They don't need that extra little uncertainty from the t distributions that spread out. They can always use the z distribution. This is a little thing to remember. So again, you're going to see, well, here we are. Yeah, we're back in the proportion world. We're using a z-stat. And we're going to compare it to a critical value from the z distribution, the norm S. And again, and everything else is going to be the same, right? So we're going to have a same sort of null hypotheses, same set, either they're equal or they're less than or equal to. We're going to form a difference, and we're going to do the same little thing, a lower tail test. Cram all the alpha there, upper tail, we're going to stuff all the alpha there, two-tailed, half of it on each side, two-tailed for the equal case, and a lower and upper tail for the less than, equal to greater than or equal. And we're going to reject it, we fall out here. And other than that, every approach is the same. So, you know, here's a proportion. Is there a significant difference between the proportion of men and the proportion of women who vote for some proposition A? They don't say what it is. So you take a random sample. We had exactly half the men and well over half of the women said they would vote yes. So here's a poll. We're inundated with polls right now. I'm sick of them, right? That's it. You got to go vote next week, right? If you haven't, I got to do my civic duty, right? Go vote. Go vote next week when we have an easy week. I already voted. I had to do early. So testing at the 5% level. So we're going to use that z-test. Our hypothesis is they're equal. Our alternative hypothesis is they are not. Here's the proportion of the men, the proportion of the women, significantly more. Looks to me like there's a difference. Let's do our pooled estimate. So here's our pooled P, our pooled proportion. 0.582 is the average proportion, right? But it's weighted to the total number. Yeah. That's a little bit closer to the mean side there. So our z-stat P1, P2, 0. Since you assume these two are equal, there was that T-bar we calculated. There's the number of samples, minus 2.2. And your critical value is 5%, plus or minus 1.96. So here's the big mistake on their view graphs, right? That's like, it clearly falls out here, and then they say, well, do not reject it. I was thinking, well, I believe it kind of squarely fell in the rejection region. So I don't know, I'm not sure what they did. So definitely reject this one, which I think was fairly evident from the data. There clearly appeared to be a pretty strong difference in the number of men versus the number of women that supported it. The two proportions were 0.7 and 0.5. And so our variability didn't get us on this one. So yeah, rejected. There is significant variance. Cross it out, yeah. So you can see, because it fell out here. It's a two-tailed test. They're putting 0.125 on each side. It's within 5%. You've got that number memorized, I'm sure. You've seen it so many times. And it's common, because it's 5%. So again, no difference. This is no different than these over here, except, well, yeah, it is different. He uses a z-test, but it's the same sort of thing. No, so we're getting there. And oh yeah, if you don't like to use the z-critic, if you don't like to look up the p, you can use a confidence interval. And if the confidence interval captures 0, it's got it. All right, so let's do the last thing. So we've covered the separate t and the pooled t based on whether their variances were equal. We covered the paired t because that was when you had dependent samples, right? That was the pizza at the same times, or the training of the guys. We covered the z because it was categorical versus numerical data. And so all we've got left is here, the design of experiments guide, the F test, the one I wanted you to know. Okay, and so the F test is there to examine what? The difference in the variances. And so you may want to ask that. That may be important. Why is it important? Well, one place it's important is right here, right? Deciding which one of the two t-tests to use. So there's one we see already. It's also important in the NOVA test, right? Analysis of variance. Okay. All right, I would say it is. So let's explore this new distribution that we haven't explored before. It's an F distribution. So we're going to test for the ratio of two population variances so we can answer this question. Are the two variances equal? Yeah, this is our big question. Okay. And so we're going to test that, we're going to look at the ratio of the two variances from the samples, S1 squared over S2 squared. And we're always going to make this F statistic bigger than 1. Yeah, I don't want to get into that again if you want to go into the math class, but just know, okay, we're going to put the larger variance on the top. So S1 is the standard deviation squared. It's the variance of sample 1, this is sample 2, and each of them have N1, N2 are the sizes. Yeah, so they got different degrees of freedom. So we've got this F test from an F distribution. And guess what? Yeah, you're going to find it from an F table. The F table has 2 degrees of freedom, one for the numerator, one for the denominator. The larger variance is always in the numerator, therefore your F stat is always greater than 1. The big one's in the top. Yeah, and in the F table, they're going to show it in 2 view graphs. The numerator degrees of freedom, pick your column. The denominator picks your row. Or we can use F distribution in Excel. Okay, so let's see. What does the F distribution look like? Aha. So it's not a symmetrical distribution. It's not like this one. So we're always going to be looking at the right side, at least in this class. Now, here's a subtle nuance that shows up in the book in the examples. They work 2 different examples, and yeah, and they're clearly showing it on the view graph, but in the book it sort of just shows up in the examples. So if you're doing an equal, the variances, your null hypothesis is that the 2 variances are equal, We do like we've done before, we only put alpha over 2 up in the tail, kind of to mimic the two-tailed thing. But if you're doing a greater than or less than or equal to, well, you won't do that because this is the one you're assuming was bigger, so we'll only do a less than. But you cram all alpha up here, okay? And again, that's just because that's to communicate with statisticians the same way as we did with the t-test, where when we had an equal situation, we only were putting half of it up in the tail. Even though you say, well, this is a non-symmetrical distribution. That's the way we're going to do it. So notice that difference, and it's in that way in the book too, in the examples. So here we go, back to the same example. So good, we treated it 3 times. So now we're going to ask ourselves, let's see, is there a difference in these variances? Okay, so that we could say maybe which one of these was the better test to use. Well, okay, let's do it. It's not hard, right? So here we're going to ask ourselves that. We're going to assume that they're equal, and our alternative hypothesis is they're not. And we're going to do it at a 5% level. So the one that had the bigger variance was the 22 sample. 25 sample had the smaller. So we're looking for f at alpha over 2, y alpha over 2, right? Because it's an equal condition. 20 degrees of freedom, that's the numerator. 24 is the denominator. So again, this is another one of those situations. If you're going to use Excel's F distribution thing, plug in one from the table. So or read the, or for goodness sakes, read the help so you know which one's the numerator, which one's the denominator degree of freedom. Or you do like me when I tried on R, because I wanted to put that in here too. I just guessed and saw what the number, and then looked. Did it come up with this one? No, okay. So anyway, in the F table, which show me I thought they had the F table in about 2 view graphs. No. Oh, it's in the book. Yeah, the book, where you can go. That's right. The book is the thing that has the F table, but not for this example. Yeah, I should have pulled it up. They show you how to read the 2 columns. So you've got different tables for the different percentages that you're putting here again, and then you've got that determined the column, that determined the row. You can go down and find these critical values. It's almost always easier to use Excel. Let's just stuff it in there, which I will on the examples. So, okay, so our statistic, there's the larger one, there's the smaller one, there's our F-stat, falls in here. Here was our critical value. So it's not in the rejection region, so don't reject it. So the conclusion, there's not sufficient evidence of a difference in the variances. Okay, so that sort of answers your question, right? We assumed the variances were, now we've not assumed it, we've actually determined that we think they're equal. So the pooled t-test would have been okay. And see, that was the one that threw it in the reject region, right? Was that when we first did that thing? Yeah. So now you have an answer, and you could say, I'll use that one because of this. Okay. So that's another way you could have approached that. And again, this F stat will show up in your NOVA, your analysis of variances, and so it's and design of experiments. And so it's an important one to know. We won't do a lot with it in this class. So what have we done? We've looked at 2 independent samples and done the pooled t-test or the separate t-test, because we could either assume they were equal or not. And we could look at t-stats compared to t-critical. We could look at a p-value if we wanted to, compare it to a percentage, or we could do a confidence interval. Three ways to decide whether to reject or not. And then we also had this world of possible related samples where we could use this paired t-test and also a confidence interval or a p in that if we wanted to. And again, why would we do that? Because we know a slight bit more about the data. We knew that this sample went with that one, and we might be able to form a stronger conclusion like the pizza problem. We were able to dig some more out of the data because we started with more information. You're not going to make something out of nothing, that's for sure. And then we did the same thing with proportions because we might have had categorical data. Still no difference, well, subtle difference, Z versus T. But the approach is the same. The comparative critical value compared to a P to an alpha, or they look at a confidence interval, either way. And then finally we learned a new thing, the F-test, which focuses only on the difference in the variances and will help us in the future understand where variance comes from. And that's where the power in the design of experiments in ANOVA comes from, because you're going to do different types of samples based on how you set your experiments up, and you're going to ask yourself how much of the variance comes from this thing or this change or this difference in the experiment, and that's going to let you know, well, does that thing matter or not? And so that's where this is going to come into play in the future. So this is, again, I think, conceptually not a giant leap from what you've had in the last two chapters. That's building on it fairly clearly. Yeah, here we go. Yeah, and so, and the techniques are similar. The distributions are the same. We're using T-disk and Z-disk. We did introduce that F as a way to look at those variances. So I'll work two problems for you, 1058 and 1066. So 1058 is kind of interesting. It's got from the American Society of Quality, a salary survey in 2011 comparing black belts to green belt salaries. And they did 141 green belts. These are their members. Black belts, I mean 26 green belts. They had a mean salary and a standard deviation. So it looks like right offhand the black belts are doing better, doesn't it? So let's ask that, right? Is there a difference in the salary variability? So let's ask that first. Why would we might ask that first? Because it might guide us into which one of these two to use. And why are we even using these? Well, they're independent, right? We didn't look at salary before black belt and after or something like that. It's just a pile of black belts in one group and a pile of green belts in the other. Okay, so our null hypothesis is there is no difference in the variability. Our alternative is there is. And group 1 is green belts, group 2 is the black belts. Why is group 1 the green belt? Remember when we did this F test, we had 1 was the one that appeared in the numerator, 1 was the one with the larger variability. Green belt has the larger variance, so make it group 1 so that when it gets in the numerator, it'll be the larger one. Okay, so let's see. So I've got all your commands in here. Here's your critical value. Notice since it's an equal, I'm stuffing alpha over 2 in the top, like I said. Your F-stat, just squaring the standard deviations. Let's see, what anything else that's, oh, there's your degrees of freedom, numerator and denominator. And so, hey, your F-stat is less than your F-critical. Don't reject it. Your p-value, if you want to desire to do it that way, was larger than 5%. Remember, the p is low, H0's got to go. So either you have a small percentage chance of it happening, or your critical value is bigger, or your stat is bigger than the critical value. So we don't reject H0. Do not reject, which means the variances are pretty much the same. Okay, we've answered this question. Let's use the pooled t-test. Okay, because there's no difference in the variance, a pooled t-test can be used. That was question B. Well, makes sense, because that was the whole reason you probably would have done question A, right? So question C now is the one you would care to ask, right? Is there a difference in the average salary? Looks like it, but let's ask it statistically. So again, we're going to say to our null hypothesis, the green belt population mean is larger than the black belt, and our alternative is that no, it's not, and we don't think it is, and we're definitely going to reject this, I think. So T critical here, it's a one-tailed test, right? Because we're using the bigger, right? So we crammed all of it. There's no divide by 2. We crammed all of it in one tail. It's one tail because it's a greater than. Here's the variance. Here's the t-stat. Same way we've always calculated the t-stat. So rejected. Yeah, p-value is teeny tiny. So yeah, the conclusion is there is statistical evidence to reject the null hypothesis that the green belt salary was bigger than the black belt. It was not. So, very simple approach, but we went through this good thing where we asked this question first and decided which one of the two tests to use. And then 1066 is back to the restaurant and the dessert and the beef question we had months ago, and we've got males and females order different amounts of dessert. And we've also got, did you have a beef entree or not? And does that have anything to do with whether you order dessert? So this is not on this side of the board, is it? This is a yes, no, dessert, not, or beef and not. So this is a z-test and categorical proportion. So right away you say, okay, I'm done with all of these questions, I don't care. Use a z-test and work it that way. So what do we want to know? Well, I don't know what we want to know. Let's see. Is there a gender-based difference in dessert proportion at 5%? Okay, well, let's see. I calculated them over here for us. So 15% of the males ordered dessert, 30% of the females did. Yeah, okay. So I pooled them together, because remember, that was how we approached this thing. It was a pool. It had a pooled proportion. You had the x1 plus x2 over n1 plus n2. Pooled them together. Our null hypothesis is that, no, that's the same, whether you're male or female. You still had the same propensity to order dessert. Alrighty. So let's see. I arbitrarily picked one to be males this time. And again, this assignment was arbitrary because it was not in the F statistic. Remember, I had to pick the one I was going to make the numerator had to be the bigger variance. This time, I just picked one. So our critical value, 1.96, y, 5%. That's in our head, right? We put it's an equal, so we're putting half of it on each side. Our z statistic, same old z statistic we've had before. Here's the zero appearing. Remember, I said because you took proportion 1 minus proportion 2, and then your assumed one, pi 1 minus pi 2, there's 0. I said I'd stick it in there for you. Hugely over in the reject region. No, there's definitely a difference between the ordering of dessert between the males and the females. That wasn't too hard to see, probably by just the data. And the p-value, yeah, it's tiny, right? Well, of course, you're minus 4.5 compared to minus 2. You're way out here. So yeah, this is 0 pretty much. Okay. And now, is there a beef-based difference? So before I scroll up, look, here's the beef proportions. 40%, 16%. The pool is 22. Looks to me like yeah, there's a beef-based difference too. So let's see. Same question. You know, same null hypothesis, same alternative hypothesis, beef and no beef. Critical value is still the same because it's still 5%. It has to be the same level. Yeah, except it's on the other side. You know, so what? You know, if it's a two-tailed, it can fail over here or fail over here. Yeah. So I knew to pick the other side because I knew which direction it was going. If you don't know which direction it's going, just use compare the absolute value, right? And then so rejected, hugely out there. So you're hugely way out. So your alpha, your p-value is really tiny. So some simple tests, simple approach, I think. Seem okay? Seems straightforward and good. Not a big leap. We're just taking the difference. But what's some subtle differences in the way you treat the difference? You know, with this guy over here. Prepared. That's important and valuable to you, and this will be valuable as we go forward. Yeah, a good chapter. What a simple chapter, right? Easy to read, short to read. And notice the nuances, though, right? Where to put the alphas. If it was a greater than, less than, or greater than question, or less than. I said, no, we only had one, or an equal. A little bit. So maybe no class next week. Don't know. We'll see. I'll let you know Monday, right? Or Tuesday.
Well, if not, we'll be sure to study.
Yes, exactly. And you'll be so distraught and sad because you didn't have class. Yeah. Yeah. No. Maybe I should just cancel it just to give you a break, right? Yeah. I'll wait to see what my brother says and see if he wants to teach that topic. But I really do want you to call him, big nerd. I want to get that possibility.
Just give us his email.
There you go. Yeah, my brother says you're a big nerd because you can't teach. I didn't say that.